So today I want to look at the product rule. Which is a method of differentiation. There's three of them: the product rule, differentiation, the quotient rule as it's called, and the chain rule. So we're going to look at the quotient rule and the chain rule next week. Maybe we'll make a start on it this week depending on how the time goes. But the first one, product rule, they're all quite straightforward once you know how they work. And I want to introduce it by way of looking at an example from the textbook and how that works along the lines of a practical problem to do with differential calculus, is what we were looking at last time. So I want to look at one of those and then see how the product rule can be used to solve it. And then we'll focus on the product rule, write down what that is, and use it. Okay? So this is an example of a practical problem. Displacement S of the end of a stiff spring at time t is given by that function, S equals AE to the minus kt sine 2 pi ft. Determine the velocity of the end of the spring after 1 second. If A equals 2, K equals 0.9, and F equals 5. This is not an uncommon function that we find in engineering. It's got two parts to it. There's an overall sine function, sine 2 pi ft. And 2 pi f we know is the angular velocity. So this is in fact the general function sine omega t, where omega is the angular velocity of something that's rotating, that's producing this sine wave. So if I were to sketch the sine wave, I might expect to see something like this, okay, with an angular velocity omega of the thing that's rotating to produce that wave. But if we look at it, we can see that in fact that's multiplied by AE to the minus KT. Now we know from our general knowledge of functions, wave functions, that if I were plotting this, this is y against t, say, y equals A sine omega t is the general function. A represents amplitude of the wave, okay? And so, if we look at this, we can see that the amplitude is another function that's time dependent. We've got two functions of the time dependence. The first one, which is something to do with the amplitude of this wave function, and then the other function is this one, which is the sine function. They've both got the variable t, the independent variable t. If I were to sketch that, what would you expect to see? If we put it on autograph, let's see what we get. So typing it in, y equals A, E, it recognises E as this natural number, oops, E, to the power minus kt, or x, we're going to have to use x there, times the sine of 2 pi fx. And that's what we get if we put it on autograph. We're going to focus on just the right-hand side of this curve because we're actually only interested in what happens after t equals 0. We're not interested in negative times because this represents times. So the function, which is behaving quite strangely on the left-hand side, luckily we're not interested in. We're only interested in the right-hand side of the function. So if I just zoom in on that a bit, we can see that I also, if I change it to default scales, we can see it in terms of pi. There it is. So let me zoom in on that. We can see So if we look at this function that we've just done an autograph, the sine function is the underlying function. That's this, the sine wave. Okay? But the amplitude of this sine wave is not fixed. The amplitude of this sine wave is an exponential decay function. There it is. Decay, as we've just been talking about, because it's negative. And exponential decay looks like that. So the amplitude of this wave is decaying exponentially, and you can see that here. Okay? The amplitude is dying off. And I'm sure you can think of situations in engineering where that sort of wave function would be in evidence. If I get something vibrating, that might be the natural way the oscillation dies away exponentially. Some sort of circuit, when it's switched on, it might behave like that until it reaches a steady state. So lots of engineering scenarios behave like this. It's some sort of wave function with an exponentially decaying amplitude. So this is not an uncommon type of function to see. If we look back at the question, we've got the displacement of the end of a stiff spring, here it is described by this. And if we plot it, it might look a little bit like this. So in other words, this spring is oscillating and over a period of time until the oscillation dies away to zero. And the function that's describing it is here. If I differentiate this, I get the rate of change of displacement with time. What's another word for that? The rate of change of distance with time is the rate of change. It's called the velocity. So if you've got some sort of question to do with displacement and time, and you want the velocity, differentiate. Okay? So I've got to take this function and differentiate it, and then find the value of that differential, which is the velocity after 1 second, if I'm given these values for the constants. Okay? So I could go back to autograph and put in a equals 2, k equals 0.9, and f equals 5. So if I do that into autograph, go back to here, go back to the constant controller, and change a to be, what was a? So a equals 2. So I can either type 2 in there or just increase it till it gets to 2. Note what effect that's having on the wave function. What else did we have? K is 0.9 and f 5. So let me just type in 5 there, it's a bit quicker. Okay, and that's what our wave is going to look like. That's what it's going to look like. And what we're interested in is what this looks like after 1 second. So if I were to zoom out on this function, or zoom in on the x-axis here, I can see there's 0.5, there's 1. So what I'm after is the rate of change of this function after 1 second. So let's just get the 1, there it is. There's 1. I'm after the rate of change of this function after 1 second. What is it about this curve that tells me the rate of change of the function after 1 second? The gradient. So in other words, I'm after the gradient, at that time, the gradient. The rate of change of the function with time. And we can use calculus to do that. So that's what this question's all about. Okay? How quickly is this thing moving after 1 second? So how are we going to do it? We take S equals AE to the minus KT times the sine of 2 pi ft. That's our function. We're given some values, so we know that A equals 2, K equals 0.9, F equals 5. So we can put those values in. S equals A, which is 2, e to the minus 0.9t times the sine of 2 pi times 5, so that's 10 pi t. So we put the numbers in, and now we've got to differentiate it. So what we're going to do now is look at the product rule, which is the way we differentiate this, and then come back and look at this question and finish the question off. Okay?